Today we're going to do an extremely quick review of some ideas about integral basis and discriminant, and we'll do so by proving the existence of an integral basis. Integral basis of what? Well, first we'll prove existence of an integral basis of the ring of algebraic integers of a number field, and then we'll prove it for a more general scenario. This is a proof in Neukirch. So let's look first at the case of a ring of integer of an algebraic number field. Ultimately, our goal is to recover unique factorization in OK, but we can't have unique factorization into prime numbers, so we get the next best thing, unique factorization into prime ideals. And the reason that works for OK is because OK is a Dedekind domain, i.e. an integrally closed Noetherian domain of dimension 1. So we need to first prove that OK is Noetherian, i.e. its ideals are all going to be finitely generated. To that end, we'll prove something even stronger. We'll prove that every ideal of it is gonna be finitely generated, not just as an OK module, but actually as a Z module. Then immediately that already said that OK is Noetherian, or if you want to go the roundabout way, then you can directly apply this theorem for OK itself. So OK is finitely generated as a Z module, but Z is a Noetherian ring, so then OK itself must be Noetherian. Okay, so let us show that every ideal I of OK has an integral basis, i.e. a Z basis. So how do we construct a Z basis? Well, the idea behind this construction is to look at basis of K over Q lying in I, and then pick the one with the smallest discriminant. That tuple is going to give a Z basis. But how do we know there is a basis of K over Q lying in I? Actually, more specifically, what we need is a tuple of n elements lying in I whose discriminant is non-zero, where n here is the degree of K over Q. We need there to be at least one such tuple so that this set is non-empty, and thus we can have the minimum element, i.e. the element with the minimum discriminant. It's actually not hard to construct such a tuple. We can simply do it by taking a primitive element of K over Q, which we will assume to be in OK, and then take an integer, non-zero integer that lie in I. Then we know that this discriminant here is non-zero because we can compute it directly. This is just the van der Monde determinant, and using that formula we know that this is just a product of the difference between the conjugates of theta. But K over Q is separable and theta is a primitive element, so the conjugates of theta are all distinct, and thus this discriminant must be non-zero. And as C0 is non-zero, this product is non-zero, as desired. But here we have use a few assumptions, so let's clarify them. First, why can we assume that the primitive element lies in OK? Well, that's because every element of K can be written as the quotient of an algebraic integer in OK, divided by a rational integer. This is because if we take any element alpha in K, then it's algebraic over Q, so it's going to be the root of some monic polynomials with coefficient in Q. Now we can take m to be the least common multiple of the denominators of these coefficients. Then if we multiply this polynomial with m to the n, we will get a monic polynomial with coefficient in z, but now with root m alpha. So m alpha must be an algebraic integer, and so alpha is the quotient of an algebraic integer over m, over a rational integer. Now coming back, by the primitive element theorem, we know that K will have a primitive element over Q. This element lies in K, so it must be of the form theta over m for some rational integer m. If this element generates K's over Q, then theta itself must generate K over Q. So we can choose a primitive generator that is an algebraic integer. Now why is it possible to find a non-zero integer lying in I? Well, there are two equivalent ways to think about it. One way is we can just take some non-zero element alpha in I. Taking norm is a good way to pass through the downstairs field. Right, so the norm of alpha is the product of alpha with its conjugate, so it must lie in I, and on the other hand norm lies in Z, so that gives a non-zero integer in Z. Equivalently, one can look at the minimal polynomial of an element alpha in I. Well, this minimal polynomial must have coefficient in Z, right? But then observe this constant term must be equal to the negation of the rest of this term evaluated at alpha, because this sum is equal to 0. So that means that this constant term must lie inside the ideal generated by alpha. In particular, it must lie in I. These two approaches are the same because this constant term is actually the norm of alpha anyway. Thus, using this element, this primitive element in OK, and this integer here, we can multiply them together, and then we see that we get a tuple lying in I, because the C0 is in I and this data is in OK. So we get a tuple lying in I, and the discriminant is non-zero. That's because this discriminant here should be equal to this discriminant multiplied with the square of the determinant of the change of basis matrix between this basis and this basis. But that change of basis matrix is just a diagonal. So its determinant square is just C0 to the n square. And this is non-zero. This is also non-zero, as we have mentioned. So this discriminant must be non-zero. And thus this set here of tuples in I with non-zero discriminant must be non-empty. So we should be able to find an element, a tuple, with the smallest discriminant. So here we're using the well-ordering property of natural numbers. Now we want to show that such a tuple would form a basis for I. Linearity independence is clear, because if they have non-zero discriminant, then immediately they are linearly independent, because the discriminant was defined to be the square of the determinant of this matrix, right? Where the sigma i's are mapped from K into C. The determinant of this matrix is non-zero if and only if the rows are linearly independent, but the relationship amongst the rows just correspond to relationship among the eta I, because the rows are just the conjugates of the eta I. And so we see that if the discriminant is non-zero, then this eta I must be linearly independent. So now we just need to show that they span the ideal I over Z. So let's take an element omega in I. Observe that we can always write this element omega as a linear combination of eta I with coefficient in Q. Observe first though that these eta I actually even form a basis of K over Q, because they're all linearly independent, right? So they are n linearly independent vectors over Q, but the dimension of K over Q is just n. In particular, observe that any n tuple with non-zero discriminant is gonna form a basis of K over Q. So if we start with omega in I, we should be able to write omega as a linear combination of this eta I with coefficient in Q. Now for the sake of contradiction, let's suppose that one of these coefficients is not integer. Let's say alpha 1 is not integer. Now we want to create a contradiction by creating another tuple, right, but with smaller discriminant. And the way we'll do that is by replacing this eta 1 with something else. Observe that when we change this basis by this new basis, right, by replacing eta 1 with omega, then how does the discriminant change? Well, this new discriminant is just gonna be the product of the determinant square of the change of basis matrix with this old discriminant. Now observe that when omega is sum of alpha I eta I, the change of basis matrix is just going to be of this form. So this accounts for omega, and then everything else stays the same. So we have identity here. And thus the determinant of this change of basis matrix is just alpha 1. So this new discriminant will be smaller than the older discriminant if alpha 1 is less than 1. But this need not be the case though. There's no reason why this alpha 1 should be less than 1. However, we could modify omega so that alpha 1 is less than 1. And this leads to our second idea. The second idea is that whenever we subtract an integer multiple of eta 1 from omega, we still stay in I. This is because omega lies in I, and any integer multiple of eta 1 should stay in I. So their difference should lie in I. And thus we can keep subtracting multiple of eta 1 from omega until the coefficient in front of eta 1 become less than 1. More formally, we can subtract from omega the multiple of eta 1 by the floor of alpha 1, i.e. the largest integer smaller than alpha 1. Then the new omega now will have the coefficient in front of eta 1 being equal to the decimal part of alpha 1, and this is less than 1. The change of basis matrix is of this form, and its determinant is this decimal part of alpha 1, which is less than 1. So coming back, this gives us an n tuple whose discriminant is smaller than the discriminant of the eta I, contradicting the minimality of the choice of the eta I. Thus our assumption must be incorrect, and thus the eta I must span the ideal I over Z. Thus every ideal I of OK must have an integral basis, and in particular, OK must have an integral basis.